Hello everyone, today we'll discuss chapter 13, namely engine friction and lubrication. Like engine heat transfer in chapter 12, the engine friction is also a parasitic process that removes some of the inputted fuel energy. And then lubrication is one of the efforts to reduce this engine friction. This is the listing topic that will be discussed in this chapter. We'll start with the friction work and then friction fundamentals and then the way to measure the friction and then engine friction data, mechanical friction component, and then pumping friction, accessories power requirement, oil consumption, and the last topic is lubricant. Not all the work transferred to the piston from the high-pressure gases is available at the drive shaft for actual use of an engine, and the portion of the work transfer that is not available is usually termed friction work. And the friction work or the friction power is sufficiently large fraction of the indicated work or power. It can be from 10% at full load and lower engine speed, and then through 50% at light load, and it will be 100% at idle or no load. So at the idle, the engine doesn't output any power. A large part of the friction losses appear as a thermal energy, and this is the energy inside the coolant and oil. This energy must be removed in the radiator and oil cooler system. So thus friction losses influence the size of the engine coolant system. These friction losses affect the maximum brake torque and minimum brake-specific fuel consumption directly. So a knowledge of friction power is required to relate the combustion characteristic of an engine, so which influence the indicated power, and the useful output power, which is called brake power. This feature is showing a schematic of the workflow within the engine. So we have an indicated work here. So this is the energy transfer from the in-cylinder gas to the piston. So this is indicated power. And then if you can see at the bottom here, it is the brake or usable work per cycle for sure that is transferred to the drive shaft. So not all of the indicated work is available at this point. So the difference of this is called the friction work. So this friction work consists of mechanical or rubbing friction, and then work to drive essential accessories, and then the pumping work. So we have a detailed information in the next slide. Okay, let's take a look in more detail about this friction work. The friction work is expanded into the following item. First is to draw the fresh mixture through the intake system and into the cylinder, and then to expel the burn gases from the cylinder and out of the exhaust system. And such friction work is called the pumping work. The second one is to overcome the resistance to relative motion of all moving part of the engine. This includes the friction between the piston ring, piston skirt, and cylinder wall, and then friction in the piston pin connecting rod small and big end, and then crankshaft and camshaft bearing and seals, and then friction in the valve actuation mechanism, and then friction in the gears or pulleys and belt which drive the camshaft and engine accessories. The third one is to drive the engine accessories. So these accessories include the water pump and then oil pump, the fuel pump, a secondary air pump if used, and this is usually for emission control, and then fan and the generator. This picture is showing a relative importance of the friction components in a naturally aspirated gasoline spark ignition engine, so SI. So the friction is broken down into several components. So we have pumping, and then piston crank assembly, and then other accessories, and then camshaft, fuel injection pump as well. So we have three different operating conditions here. On the most left here, it is 1800 RPM 2 bar, so this is light load. And then on the middle here and on the most right side here, it is at 6 bar, 1800 RPM, and then this one is 4 bar, 3600 RPM, so this is a mid load. So first of all, let's take a look on the pumping work component. So it is this one. Let me use a red color here. So this one is the component to pumping. So it has a high pumping work losses here, and this is because of the naturally aspirated type engine. And then piston crank assembly also have a decent portion here, so can be around 25 to 30%. And then we also have the friction here inside the camshaft, as well as this one is other auxiliaries. And then you can see also here, as we increase the engine power, so from 2 bar to 6 bar, the percentage of this friction decreases. And then also shown in this data is the relative importance of the friction component for a small turbocharged diesel engine. So let me give a blue here. So CI, this one is for a small turbocharged diesel engine. So an important characteristic of this turbocharge is that, as you can see in here, that the losses due to pumping is much smaller. So you can see in here, if you compare with the SI. So as we increase the engine load, it will be smaller, and at some point it will be positive. So it means it will disappear completely. And then another thing what you have for this CI is that because we need to have a injection system, there will be a losses that it's used to supply the energy for the fuel injection system. So it is, let me use a purple. So it is this one. So this one is not in the SI engine, okay, because this is a typical for a diesel engine. This is the terminology that will be used in discussing engine friction in this reference book. The first one is pumping work, or WP. So this is the net work per cycle done by the piston on the in-cylinder gases during the intake and exhaust stroke. And this WP, the pumping work, is only defined for 4-stroke cycle engine. It is the area of B in figure 2.6, so it's chapter 2, and I copy the figure on the top right of this slide. And you can see in here that the pumping work is denoted by B here, okay. And then the second one is mechanical friction work, or WMF, okay. So MF here stands for mechanical work. So this is the work per cycle dissipated in overcoming the friction due to relative motion of adjacent components within the engine. So I've shown you in the previous slide. So we have several moving components in the engine. So like piston ring, piston skirt, and cylinder wall, and then piston pin, connecting rod, and then crankshaft and camshaft bearing, and then friction in the valve actuation mechanism, and so on. The next one is accessory work, or WA. So this is the work per cycle required to drive the essential engine accessories. So we have oil pump, fuel pump, fan, generator, and so on. And then we have a total friction work, WTF. So TF here stands for total friction. So this is the sum of the pumping work and then mechanical friction work, and then the last one here is the accessory work. And then it is often useful to discuss the difference between indicated and brake output in terms of the mean effective pressure, so MEP. So therefore we have IMEP and then BMEP. So this is the formula that is used to correlate between MEP and work. So imagine you will also have such MEP for the friction work. And then this is the correlation to correlate between power and MEP. So power equals to MEP times VD. VD is the engine displacement, and then N is the engine speed, and R is the number of revolution per cycle. For the indicated output, we have what is called gross indicated mean effective pressure, or IMEPG. So G here stands for gross. This is the work delivered to the piston over the compression and expansion strokes per cycle and per unit displaced volume. The second one is what is called net indicated mean effective pressure, IMEPN. Okay, N stands for net. So this is the work delivered to the piston over the entire 4 strokes of the cycle per unit displaced volume. Okay, from this one, you will see that the difference between the gross and net is the pumping work. Okay, this is equation 13.2. IMEPG equals to IMEP net plus PMEP. So this one is the MEP due to the pumping work. Okay, the next one, we have TFMEP. So this is the MEP due to total friction. This is the sum of PMEP and then MFMEP. So this is MEP due to mechanical friction. And the last one here is due to the accessory work, so AMEP. And then we also have correlation 13.2c, BMEP equals to IMEPG minus TFMEP. And then we also have one more correlation that is very popular and usually used in real engine application. So we have BMEP, okay, equals to IMEPN, okay, and this one is minus FMEP. And following the correlation or following the terminology in the reference book, this one is the sum of MFMEP and AMEP. Okay. And then for turbocharged 4-stroke engine, we don't have the pumping losses. In fact, the pumping work is a positive work. So this is an addition work to the work generated by the engine during expansion stroke. So we have correlation 13.2D, IMEP net equal to IMEPG plus PMEP. So this is positive work. And then the FMEP is just the sum of the mechanical friction MEP and accessories MEP. And then BMEP equals to IMEP net minus TFMEP. And TFMEP once again is the sum of these two. Next topic is looking at the friction fundamentals. The friction losses can be classified into 2 groups depending on the type of dissipation which occur. The first group is between 2 metal surfaces in relative motion with a lubricant in between. Okay, and then the second group is what is called dissipation in turbulent flow. So we will look at these 2 groups in more detail in the next slide. A primary problem in understanding friction between lubricated surfaces in engines is the wide variation in the magnitude of the force involved. And then we might encounter a different regime of lubrication. This figure is showing two common geometries for lubricated part. On the left side, we have what is called a journal bearing that is lubricated. So the journal is rotating, so with a certain speed, and then we have the load with this direction, and then between the journal and bearing there will be a supporting oil film with a certain thickness. And then on the right side we have a kind of sliding bearing. So we have a bearing here, and then a load here, and then we have a path, and then between this path and a bearing there will be a supporting oil film. The different regime of lubricated frictions are illustrated by the strip-back diagram as shown in this figure. So the vertical axis is the coefficient of friction F, which is defined as the ratio of tangential force to the normal force. And then it is plotted as a function of what is called here is dimensionless duty parameter. So this is mu n per sigma. So mu here is the dynamic viscosity of the lubricant, and then n is the rotational engine speed, so or rotational speed of the shaft, and then sigma is the loading force per unit area. So for the sliding surface, we have a different dimensionless duty parameter, but it is similar. So you have mu u over sigma times b. So u is the relative velocity, so it's replaced n. And then b is the length of the sliding path in the direction of motion. So let's take a look on this strip-back diagram. For a small duty parameter, so the regime is usually it's called boundary lubrication. So this is close to solid friction, so it is represented by Fs. So this is a metal to metal contact type friction. So there is no lubrication between two metals. And then as the engine duty load is increased, then we will enter what is called here is mixed lubrication regime. So some part might still have metal to metal interaction, but other part might already have a lubrication in between. And then as the load is increases, then we will enter what is called a hydrodynamic lubrication. So it's mean between two metal surface there are fully lubrication. So as you can see in this figure, the coefficient of friction F, it will equals or it is close to Fs for lower load, and then in between it will be the weighting factor, or it will be a kind of a weighting average between Fs and Fl. So Fl is the hydrodynamic friction coefficient. The coefficient of friction F can be expressed following equation 13.3. So F equal to alpha times Fs plus 1 minus alpha times Fl. So Fl is the hydrodynamic coefficient of friction, and then Fs is the metal to metal coefficient of dry friction. And then alpha here is the metal to metal contact constant. So this alpha vary from 0 to 1. So if it is 1, then we have a completely metal to metal interaction. If it is 0, then we have a lubrication between the two metal surfaces. As alpha approach 1, then F also close to Fs, and the friction is called boundary friction. So as you saw in the strip diagram in the previous slide, so it's happened when the load is low, it's small. So this is close to solid friction. So the lubricating film is sufficiently thin that it cannot prevent metal to metal contacts between surface asperities. And then as alpha close to 0, then F will be close to Fl. And the friction is called hydrodynamic or viscose or thick film lubrication. So in this case, the lubricant film is sufficiently thick that it separates completely the surfaces in relative motion. Under boundary lubrication condition, the friction between the two surfaces in relative motion is determined by surface properties and by lubricant properties. Surface properties are roughness and then hardness, elasticity, plasticity, shearing strength, and then thermal conductivity and wettability with respect to the lubricant. And then lubricant properties are mainly surface ones or chemicals ones, which govern the ability of lubricant and then additive, if any, to attach themselves to the solid surface. This feature is showing the schematic of two surfaces in relative motion under boundary lubricant. So you can see in here there'll be oxide layer and then absorb film, and this is the real area contact, and this is the this happens under boundary lubrication condition. And then hydrodynamic lubrication conditions occur when the shape and relative motion of the lubricated sliding surfaces form a liquid films in which there is sufficient pressure to keep the surface separated. And the resistance to motion here is result from the viscous shear force within the liquid film. And I think you know this formula in fluid mechanics class, that the shear stress, this one is a function of this mu, dynamic viscosity, and the gradient of the velocity, dv over dy. So the friction coefficient, this is once again the ratio between shear stress and normal stress, will be proportional to this parameter, so viscosity times speed over loading. So this one is independent of the material or roughness of the part. The next type of friction work is turbulent dissipation. So part of the total friction work is spent on pumping fluids through flow restriction. So the cylinder gases, cooling water, and oil are pumped through the engine, and there will be flow losses along the passage. And then we also have a fan that pump air through the engine radiator. So work is dissipated here to drive turbulent viscous flow, and then the pressure difference required to pump this fluid around the flow path is proportional to rho time square of velocity. So you keep mind for this type of the friction work, we have a square velocity dependency. Okay, and then because the flow velocity is correlated linearly with the engine speed, so this type of friction work will be proportional to the square engine speed, so square n. The friction work will be given by integrating the friction force Ffi times its displacement dx, so this one. And then the friction force components are either independent of speed, so this is when we have a boundary friction, proportional to speed, so when we have hydrodynamic friction, or to speed square, so it is for turbulent dissipation type friction work. So that we can write it down, the correlation between the friction work to the engine speed. So we have equation 13.5. So this one to represent the boundary friction, this one is for hydrodynamic friction, and this one is for the turbulent dissipation type friction. Next topic is a measurement method. A through measurement of friction in a firing engine can only be obtained by subtracting the brake power from the indicated power determined from accurate measurement of cylinder pressure through the cycle. So this is doable for a single cylinder engine, but it's not easy to be used for a multi-cylinder engine due to two reasons. The first one is because of cylinder to cylinder difference in indicated power, and the second one is due to the difficulties in obtaining sufficiently accurate cylinder pressure data from each cylinder. So as a result, friction is often measured in a motored engine. Motored engine, it's mean we run the engine without combustion, so we crank the engine using external mean. There are several measurement methods. So the first one is measurement of MMEP from IMEP. So in this case, the gross indicated mean effective pressure is obtained from the integration of PdV over the compression expansion stroke for a 4-stroke engine, and then over the whole cycle for the 2-stroke engine. But this one required an accurate and in-phase pressure and volume data. And then by subtracting the brake mean effective pressure, the combined mechanical or rubbing friction plus auxiliary requirement FMEP, so MEP plus AMEP are obtained. The second method is direct motoring test. I have a detailed explanation for this type in the next slide. And then the next one is what's called a Willian line. So in this case, an approximate equivalent of the direct motoring test for diesel engine can be obtained. And this feature is showing an example of Willian line method for determining friction mean effective pressure. So in this case, a plot of fuel consumption versus PMEP, okay, can be obtained from the engine testings at fixed engine speed, and then by doing an extrapolation. So extrapolation, and then you will get somewhere here, and this is where we have a motored FMEP. But it is not easy because generally the plot has a slight curve, making accurate extrapolation be difficult. And then the next method, which is called Morse testing. So in this Morse testing, individual cylinders in a multi-cylinder engine are cut out from firing, and then the reduction in brake torque is determined while maintaining the same engine speed. So care must be taken to determine that the action of cutting out one cylinder does not significantly disturb the fuel or mixture flow to the others. So for the motoring testing, the testing is under the condition as close as possible to firing. So it's mean the engine temperature should be maintained as close as possible to the normal operating temperature. So either we can heat the water and oil flow, or by here it's called conducting a grab motoring test. So where the engine is switched rapidly from firing to motor operating, and then the power required to motor the engine include the pumping power. And then in test of SI engine at part load, so the throttle setting is left unchanged. We can also do such testing on a progressively disassembled engine so that we can identify the contribution of each major component that makes the total friction losses. Although the condition during motoring testing is set up to be as close as possible to the firing case, there are still some deviation from the firing case. Number one is that only the compression pressure and not the full firing pressure acts on the piston rings and bearings. So this will impact the mechanical friction work. And then piston and cylinder bore temperature are lower in motor operation. So, and then piston cylinder clearance are greater during motoring operation, which tend to make the friction lower. However, in friction operating condition, the lubrication of the top liner near the top of the stroke is inadequate to maintain normal hydrodynamic lubrication with the high gas pressure behind the ring. So overall, the net effect of lower piston and cylinder temperatures during motoring is unclear. And then the next one is that in a motor operation, the exhaust blowdown phase is missing, okay? And the gases discharged in the later part of the exhaust stroke have a higher density than under firing condition. And then the next deviation is that when motoring, net work is done during compression and expansion stroke because of heat loss from the gas to the wall and because of the gas loss through blow-by. So this work is not part of the through total friction work and should not be deducted from the indicated work of the firing engine. And surprisingly, although we have such a deviation, the net difference is small. Therefore, this motoring testing is still used on estimating the engine friction work.